This video covers our worksheet on polarity review. In particular, we're going to be taking a look at reviewing polar versus nonpolar bonds, and in our next video, we'll take a look at polar versus nonpolar molecules. So as a review, when it comes to chemical bonding, and so this came from your first semester chemistry, you can look back and review chemical bonding. When it comes to chemical bonds, there are two primary types. We have ionic bonds and covalent bonds. With our ionic bonds, remember that ionic bonds are going to occur between metals and nonmetals. They're going to involve the transfer of electrons. That electron transfer produces ions, and ions are going to attract to one another through opposite charges, forming a bond. That attraction is going to result in ionic solids, which are going to be a three-dimensional network of many ions attracted to one another. Now, our covalent bonds, they're going to be our most common type of chemical bond. They occur between two or more nonmetals. They involve electrons being shared. That sharing is a result of orbital overlap. So again, you would have covered that in your first semester chemistry class. So we're going to have overlap of our orbitals. They could be atomic orbitals, they could be hybrid orbitals. But when those orbitals overlap, the electrons get shared between the two nuclei. The electrons become attracted to the nucleus of the neighboring atom, and that attraction forms our bonds. And these bonds result in molecules. So if we take a look at some of our problems, we've got to be able to identify our bond types. That's going to be the foundation of just about everything we do this semester. We've got to start being able to identify, do we have covalent or ionic bonds? And the key to that is identifying metals versus nonmetals. So if we recall our periodic table, all of our periodic tables are going to have kind of that zigzag or that staircase that runs through them. Our metals are going to be those substances that are going to lie to the left of that zigzag or staircase, with the exception of hydrogen. Hydrogen's all the way over to that left, but hydrogen is not a metal. Our nonmetals are going to lie to the other side of that zigzag, so it's going to be all the materials to the right of that zigzag or staircase plus hydrogen. Now, if you have a hard time remembering right from left, you can always just look at your periodic table. Use some of your daily knowledge. You are familiar with certain metals. You're familiar with things like silver and gold and copper. And if we look at our periodic table, we can see that those elements are located on the left side of that zigzag. So all of the materials on that left side, again, except hydrogen, are going to be metals. And again, you're familiar with some nonmetals. You breathe in oxygen. You know that that is not a metal. That's that gas that we're breathing in. And so again, you can use some of your daily knowledge if you can't remember that left from right. So again, we've got to be able to identify ionic versus covalent. So when we look at a chemical bond, how can we distinguish ionic versus covalent? Well, we've got to look at the types of elements present. Ionic, we said, was going to occur between metals and nonmetals. So we look at that formula and we see at least one metal present. It's going to be ionic. Covalent, we said, occurs between only nonmetals. So if we look at that formula and there's only nonmetals present, then we have covalent bonds. And so again, being able to identify covalent versus ionic, this is a foundation of this course. We have got to be able to identify ionic versus covalent, which comes down to identifying metals versus nonmetals. So looking at problem number one, here, or this is actually problem number 3, we're being asked to identify if these substances contain ionic bonds, covalent bonds, or both. So if we look at NH3, we've got nitrogen and hydrogen. These elements are both lying on that right side of the zigzag, so they are all nonmetals. So if my compound consists of all nonmetals, then it is going to contain covalent bonds. And since it contains covalent bonds, this compound is a molecule. Now next we've got calcium bromide. I look at my first element and I see calcium. Well, calcium is located in group 2A. So that's over to that left side of the periodic table. Calcium is a metal. As soon as I see that metal present, I can go ahead and it's listed in that first location, that cation location. That lets me know I've got an ionic bond. So that calcium bromide is an ionic compound or an ionic solid. Next, we've got sodium hydride. So again, I look at my first element and I see sodium. And sodium is located in group 1A of my periodic table. So it's over there to that left side, making that sodium a metal. Again, the instant I see that metal out front, I have an ionic bond. So again, that sodium hydride, it is an ionic solid. Next, I've got this H2SO4. So I've got hydrogen, sulfur, and oxygen. Hydrogen, sulfur, and oxygen, they all are over on that right side of the periodic table. So they are all nonmetals. Since they are all nonmetals, that substance contains covalent bonds, and H2SO4 is a molecule. And then finally, I've got this sodium nitrate. So we've got to be careful here because I've got more than two elements. The first thing I see is that sodium, which is in group 1A. And since that sodium's in group 1A, it's a metal. And so that sodium cation is being attracted to this nitrate anion. That bond between the sodium cation and the nitrate anion is an ionic bond. However, that nitrate, that unit consists of bonds between nitrogens and oxygens. It's a polyatomic ion. Polyatomic ions are groups of atoms held together typically by covalent bonds. Nitrogen and oxygen are nonmetals. So that NO3 minus is all nonmetals. So the NO3 minus contains covalent bonds. So that particular compound is going to be a mixture. The polyatomic ion is composed of covalent bonds, but that substance happens to have a charge that can then attract that sodium cation, and the attraction between those charges is going to give me my ionic bond. So we have our two bond types. We can be ionic, in which we're transferring electrons and we're getting the attraction of ions, or we can be covalent, where we are sharing electrons and we have the attractions of electrons between our nuclei forming our bond. Now, the next thing we're going to take a look at is bond polarity. When we talk about, and this is going to refer specifically to a covalent bond. A covalent bond can be described as being either polar or nonpolar, and this is going to be based on how the electrons get shared. Whether the electrons get shared equally or unequally depends on electronegativity. Remember that electronegativity is going to be the attraction an atom has towards shared electrons. So you would have covered this again first semester chemistry when you would have talked about chemical bonds and you talked about your periodic trends. Recall that when it comes to electronegativity, that fluorine is our most electronegative atom. So the closer an atom is to fluorine in the periodic table, the more electronegative it is. So for example, oxygen, which is right next to fluorine, is more electronegative than nitrogen, which is more electronegative than carbon. The greater the electronegativity, the stronger that individual atom has, the stronger attraction that individual atom has for electrons. So when it comes to nonpolar bonds are going to be the result of equal sharing of electrons. This is going to occur when two atoms have the same or similar attraction for the electrons. So when that's the case, we have either a small to no difference in electronegativity, resulting in atoms being shared, or electrons being shared equally. Now, this small to no difference in electronegativity, this is going to occur either when we have bonds between identical atoms, so they have the exact same electronegativity, the exact same attraction, or carbon-hydrogen. So when you guys would have talked about this before, you would have gotten into actually calculating electronegativities, and the carbon-hydrogen electronegativity difference is considered to be in that small range. And since it's in the small range, it's a negligible difference. So essentially, carbon and hydrogen are sharing those electrons equally. This gives our atom an even distribution of the electrons being shared. So in our figure here, if we have a 0 electronegativity difference, we get a covalent nonpolar bond. Electrons are shared equally. And that is what this image is representing, is our electrons being shared equally. The electron distribution, so the purple color, is being spread evenly across both atoms. Now, our other type of covalent bond is the polar bond. This results when we have an unequal sharing of electrons. This occurs when two atoms have different attraction to the shared electrons. That arises when we have a significant electronegativity difference between the two atoms. Generally, not always, but generally this occurs between different atoms other than carbon and hydrogen. So we're going to keep this simple for right now. We're going to consider carbon and hydrogen our exception, and we can assume for the compounds we'll encounter that everything else is going to be polar. Now, this uneven sharing of electrons results in an uneven distribution of the electron density. So we can see that in our image here. So if we have an electronegativity difference of 0.4 or higher, so actually between 0.4 and 1.8, that's going to be considered a covalent bond. So we have a significant electronegativity difference. We have a polar covalent bond. Electrons are shared unequally. So that's what we're seeing here in this electron density map. So we've got our two atoms, but the electrons are being more concentrated on one atom than another. This occurs with the atom that has the greater attraction to the electron. So the atom with the greater electronegativity pulls the electrons towards itself because it's more attracted to them. As a result of having that negative charge being pulled towards one end of our bond, it's going to generate a partial negative charge. The atom with the weaker attraction, which has less of the electron density, becomes partially positive because the electrons are moving away from that. Its nuclear charge, those protons become more prevalent, and we get a partially positive charge. When that's the case, when we've got a bond between different atoms in which one atom's got that stronger electronegativity, we're going to represent that uneven distribution using what we call a dipole arrow. The dipole arrow looks like an arrow with a hash mark on its tail. It starts on the less electronegative atom and it points towards the more electronegative atom. So our less electronegative atom is going to be that one with that partial positive. So here we have the starting of our arrow, and it's going to point towards the more electronegative atom. This is going to be another foundational piece of this course. We've got to identify, are our bonds ionic or covalent? If they're covalent, we've got to identify, are they polar or nonpolar? Because this is going to impact everything we talk about this semester. So if you look at some examples, we've got some bonds, and we're being asked to determine, are these bonds polar or nonpolar? So if we look at this carbon-nitrogen bond, it's a bond between different atoms. So we said for now, we're going to assume if they're different, other than carbon-hydrogen, that they're going to be polar. So that carbon-nitrogen bond is going to be polar. Next, I have oxygen-hydrogen. Again, I have a bond between different atoms. So we're going to assume if the atoms are different, the electronegativity difference is large enough that that will be a polar bond. Then we have carbon-hydrogen. Carbon-hydrogen is our one exception that we've got to know. Carbon-hydrogen electronegativity difference is too low that it is negligible. So this is a non-polar. So we've just got to know the carbon-hydrogen bonds are non-polar. And then finally, my hydrogen-hydrogen bond. I've got a bond between same atoms. So they have the same attraction for the electrons. So that will be non-polar. So as we've said already, that if we've got a polar bond, we're going to represent that polarity difference using partial charges, partial positives, partial negatives. We're also going to use dipole arrows. So for problem number 5, we're asked to go back to our polar bonds and indicate their polarity using partial symbols and drawing dipole arrows. So our polar bonds were in A and B. So we'll go ahead and start by placing the partial positives and partial negatives. And to do that, we've got to look at our electronegativities. We've got to remember our electronegativity trends. So our periodic trends tell us that as we go across a row, electronegativities increase, except for group 8A. As we go down a group, the electronegativities decrease. So we've got carbon and nitrogen. They are located in the same row, so we can use that periodic trend moving across the row. Nitrogen is further to the right, making the nitrogen more electronegative. So we said that the more electronegative atom is going to get our partial negative charge. That's going to leave my carbon partially positive. So our dipole arrow starts on the positive atom and it points towards the negative atom. So doing the same thing with B. My oxygen is further to the right in the periodic table, so it is more electronegative. So the oxygen is negative, the hydrogen is positive. So this time we start on the hydrogen and we point towards the oxygen. So we've got to be able to look at bonds and identify them as being polar or nonpolar. Identify who's more electronegative so we can place our partial positive and partial negative charges, and then be able to draw our dipole arrows. So looking at problem number 6, we've got a series of bonds, and we're asked to rank the bonds in order of increasing polarity. So here we're looking at electronegativity differences. And so when we're looking at those electronegativity differences, again, we're looking at our trends. Here we've got bromine, chlorine, fluorine, and iodine, all bonded to hydrogen. So we're going to look at their differences in electronegativities. What we're going to find, so these are all in the same group. And remember, our trend is that as we go down a group, that electronegativity is going to decrease. So as far as my trends go, my fluorine is the greatest electronegativity, followed by chlorine, bromine, and then iodine. And so my bond polarity is going to follow this same trend. So that means that my HI is going to be the least polar, followed by my HBr, my HCl, and my HF. So my HF is going to be the most polar bond. My HI is going to be the least polar. So if we're looking at bonds, we're looking at our electronegativity trends. The greater the electronegativity difference between the atoms, the more polar that bond is going to be. So here in problem 6, we had nonmetals all attached to hydrogen. If we look at problem number 7, all of these bonds, we're going to have atoms connected to carbon. So again, we're looking at the electronegativity of the different atom. So we're looking at fluorine, nitrogen, oxygen, and carbon. These atoms are all in the same row. So again, as we go across the row, the electronegativity increases. So that means my carbon is going to be the least electronegative, then my nitrogen, my oxygen, and my fluorine. So again, my bonds are going to follow that same trend. The carbon-carbon bond, which is non-polar anyways, because it's a bond between two atoms, it's going to be my least polar. Followed by my carbon-nitrogen, my carbon-oxygen, and then my carbon-fluorine bond is going to be my most polar. So here we've taken a look at identifying our bond types. Are they ionic or covalent? Based on do they have metals or nonmetals? If we've identified a bond as being covalent, we've got to further identify it as being polar or nonpolar. And so we've looked at that, identifying polar versus nonpolar. So do we have same atoms or carbon-hydrogen? That makes it nonpolar. Do we have different atoms? That makes it polar. And then we've compared polarities by looking at electronegativity differences. Now this is going to tie into our next video where we're going to use this to determine if molecules as a whole are polar or nonpolar.